Let's solve projectile motion. The mass of projectile is m, is a particle which was fired from this place by velocity v0 at time 0. Let's consider. We have here some size of this step, height and thickness, h and b. There is an angle of elevation, and v0 is the initial velocity. We would like to calculate acceleration, velocity and displacement of that particle. So first we should make is to define a coordinate system we will use. For this kind of task, the Cartesian system is most suitable. So we can place it anywhere we want. For example, we can place the coordinate system here, or we can place it here, or, because I would like to show you more general case, we will place the coordinate system to this position with origin placed here at this point. Next, we need to draw a free body diagram. We expect the trajectory of the particle will be like this. So for free body diagram, we select the general position, so somewhere in trajectory. So I draw particle m, and first I add forces acting to this particle. So basically it is gravity force G, and this is in fact the only external force acting to this particle. So now we can add D'Alembert's force, inertia force. So in accordance with definition that D'Alembert's force D is minus ma, so it has this size and the orientation is against positively oriented acceleration. So because we are in two-dimensional system, we can define D'Alembert force by its components, so dx, dy, where dx will be m by ax and dy is m by ay. Please make difference between vector definition and size of the vector. Okay, so this is a vector definition. So we add y component of D'Alembert force. Here it is against positively oriented acceleration in y, and there is no external force in x-axis, so the only force we can draw here is D'Alembert component, which direction is against positive orientation of acceleration. So now free body diagram is done. Generally, we can write vector equation of force equilibrium. Most general form is that sum of all forces acting on the body or particle plus D'Alembert force is 0. In our case, we can write that G plus D is equal to 0. Because we work in two-dimensional Cartesian system, we can make two component equations in direction x and y. So in x direction we write dx is equal to 0, and in direction y we can write dy plus g is equal to 0. For force specification we can use this. Dx is and dy is, and g, size of g is m by g. So this is force specification. Force specification. So we can substitute this into this system. So after substitution we write m by ax is equal to 0 and m ay plus mg is equal to 0. We can cancel mass in all cases, so finally we get ax is equal to 0 and ay is equal minus g. We can continue with these results in further calculation. So for calculation of velocity, oh sorry, it's second, because for first we have results here. Okay, it's a first task, acceleration. So second, velocity of particle. So we start with definition that acceleration is derivative of velocity with respect to time, and in this case we can calculate independently both direction ax and ay. So x direction. So we can use definition that ax is dvx over dt, and we know that acceleration in x-axis is 0, so velocity is constant in x direction. So we can say that dv over dt is 0, and we can separate variables, so we can write that dvx, so separation is made by multiplication of both sides of equation by dt, is equal to 0. We add integrational sign, and everything multiplied by 0 will be 0. So I add, so I can, if you want, I can do it. So in time 0 the initial velocity is v0 by cosine alpha, so it's x component of v0, and there is general size of v. After integration we get this. So Vx in t is V0 cosine alpha, so it is constant. In y direction, in y direction, we will continue analogically. So ay is dy dvi's over dt, and we know that this is then equal minus g. It's an acceleration in y direction. So we can multiply it by dt, so we get dvy is equal minus g dt. When time was 0, initial velocity was v0 by sinus alpha, and when time is instant time, so there is an instant velocity. So from this we get that Vy in time is V0 by sinus alpha minus gt. Okay, so this is another result. So we have Vx and Vy in time. Now let's continue with displacement in time for x direction. We use the definition that velocity in x direction is dx over dt, and from previous calculation we know that it is equal, and I'm looking to previous paper, so it is v0 cosine alpha. v0 cosine alpha. So after separation we multiply it by dt, we get dx is equal v0 cosine alpha by dt. Because v0 and cosine alpha are constants for all the process, we can put them out the integration, and we set our lower limits. When time was 0, initial position was b with respect to origin of coordinate system, and there is instant time and displacement in instant time. After integration we get xt minus b is equal v0 cosine alpha dt. Xt is equal b plus v0 cosine alpha by t. Okay, so we have displacement in x-axis and y direction. In this solution we can use the definition that Vy is dy over dt, and from previous calculation we know that it is equal, it was v0 sinus alpha minus gt. So we separate variables like this, put it to the brackets and multiply it by dt. Okay, we add integrational signs and we define lower limits. When time was 0, y was age, and in instant time we have instant position in y direction. So after integration we get h plus v0 sinus alpha by t minus a half of gt square. So finally, for example, for trajectory calculation, we have two equations, this one and this one. So we have a system of two equations, and by mutual substitution we can get, for example, function depending on x. So by eliminating time, so we can get this curve.